All right, guys, so today we're going to talk about functions, right? Yes. No surprise there. We were talking about functions last lecture, and I guess we'll keep talking about functions for a while, even when we talk about calculus, because calculus is all about studying functions, right? In some sense. So today we're going to talk about a few special functions, functions that I will assume that you're familiar with. So I'm going to introduce them to you so you remember them. And we will also talk about how to transform one function into another. So if you have a function, how can you change that function? For example, we're going to talk about translating functions to the left, to the right, up and down. And we're going to talk about stretching functions, stretching them out, squeezing them in vertically and horizontally. And then we'll talk about composing functions one with the other and see what happens. Okay? So anytime, please feel free to raise your hand and ask me a question. I don't bite. And so we're going to start with a certain type of function. Probably the easiest one is linear functions. So linear functions are called linear because they look like what? They look like a straight line, that's right. So we're going to draw a Cartesian plane with the x-axis and the y-axis. Remember, the x is the input of the function, y is the output of the function. And we're going to draw a line. And this line is going to have the equation f of x equals ax plus b. Okay, so remember, there's multiple ways to represent a function. And in this case, we're drawing the graph of the function as one way to represent it, and we're drawing the equation of the function as a different way to represent the same function. So for example, in this case, we have, let's say that this is 1, 2, 3, 4, and the same thing here, 1, 2, 3, 4, and so on and so forth. So who can tell me what b would be in this case? Yes? 2. Okay, great. Why is that? Because it's the y-intercept. If you didn't know about the y-intercept, how can you figure it out from what we said in the class before? You know, if you didn't know that as a rule, how would you figure it out? What is it? Exactly. Exactly. The equation tells you what f of x is for any x. So for example, if you plug x equal to 0, right, then f of x should be b. A times 0 times plus b, that's b, right? And you can see in the graph that that value, f of 0, is what? Is 2, right? So there you go. So b is 2. In general, b is always the y-intercept. Okay, what about a? What is a? A is the slope. What is the slope in this function right here? Let's say, just for the sake of the argument, that this point is the point 4, 4. Okay? You can almost see it right there. So the slope of this function is 1/2 because I go over by 2 from here to here and up by 1. We'll talk a lot more about slopes later, so I'm not going to be too picky about slopes right now. Just remember that the a tells you information about how inclined the function is, what the slope of the function is. Okay. So in this case, it would be, in this case, I'm going to write b equals 2 and a equals 2 over 4 is 1/2. Okay, awesome. That's as much as we're going to talk about linear functions for now. We're also going to talk about polynomials. Now, a polynomial is a function that looks how? What is a polynomial? Has curves, yes. What else? Yes? Multiple terms, that's right. And each term has a special form too. Okay, so it's a little hard to describe. I'm just going to give you an example here. For example, it could be x squared plus 2x minus 7, let's say. Okay, so polynomials are functions that are made up of adding and multiplying x. Multiplying x with itself or with other numbers. Right, so for example, we're multiplying x by itself, so x squared. Then we're multiplying x times 2, and then we're adding up the whole thing together. And then we add 7. So anything that you can make up just by multiplication and addition is a polynomial. Another polynomial could be the polynomial p of x equals x to the 10, let's say, minus x to the 3 plus x minus 1. Okay? The degree of the polynomial is the largest exponent showing up in the polynomial. So I'm going to mark this as the degree. Degree. So the bottom one is a polynomial of degree 10. And the top one is a polynomial of degree 2. So let me give you an example of these polynomials. We're going to draw one of these polynomials. P of x equals x squared minus 2x plus 1, which, if you factor it out, and this is pre-calc, so I'm not going to spend too much time on this, but you can factor this out as x minus 1 squared. Right?
Yes.
Okay. How do you know that x minus 1 squared is equal to that? Well, you said, we talked about, we didn't talk about this, but there's this binomial formula, right? A minus b squared equals a squared minus 2ab plus b squared. And that's an example of that. So if I wanted to figure out how this function looked like, and I had no idea how to do it, I can start by making a small table of values of the function. You can do this with absolutely any function you want. If you want to figure out how it looks like, just start with a table. It's easy to do. So you said, for example, x equals 0. And so what is p of x in that case? So 0 squared minus 2 times 0 plus 1 is 1. What about 1? So 1 squared minus 2 plus 1 is 0. And what about 2? Goes to 1. That's right. So then the next thing you do is you go to your Cartesian plane. And you put the points in there. So for example, in this case, let's do 1, 2, 3. 1, 2, 3. And we put the point 0, 1 in there. Where is the point 0, 1? On the y-axis, that's right, the point 0, 1. So we know because the value of x at 0 is 1, we know that the graph of the function goes through that point, right? What other point does the function go through? 1, 0, right? 1, 0. It's also on the function. What about the point 2, 1? It's also on the function, right? So then, once you have enough points, you draw a graph that goes through all the points. Now, there's many different graphs that go through those 3 points. But I also know that because this polynomial is of degree 2, it has to be like a parabola, right? So I draw a parabola that goes through those 3 points. And that's the graph of my function. There you go. Okay. So those are polynomials. There's another type of function. We're going to call them power functions. Not to be confused with the Power Rangers. So f of x, that was bad, I know, equals x to the n. That's right. So what about x to the 1? X to the 1 is just x. It's a line, right? Okay, that's right. X to the 1. It's when it's a linear function. That's right. So linear function. What about x to the 2? It's a parabola. That's right. What about x to the 3? What is it? That's right. It's a cubic line like this, and you can keep going, okay? What about if I do n not a natural number, but let's say we talk about x to the 1/2? What is that equal to? It's the same as square root of x. And that function looks how? Okay, it's a little bit like a parabola, but horizontal, right? Now, here's something interesting happens. Do I also draw the bottom part? Do I draw a whole parabola here? Okay, why not? Yeah, but why? Well, yeah, but how about in terms of what we talked about last time? Yes?
If you do the vertical line test, it goes through the
Right, exactly. It would not be a function, okay? We talked about functions last time as mathematical constructs that to each element, x, assign one value, y, right? So if we drew the whole thing, you would have, for some values of x, you would have two different values of y. In other words, the vertical line test would be violated, right? And it's not a function. So because of that, we define square root of x as the positive square root, right? You can also talk about the square root of 4 to be minus 2 in the sense that minus 2 squared gives 4. Okay, but that's not how we define square root of 4. Square root of 4 is 2 because it's the positive number such that its square is 4. Okay? So bottom line, forget about the bottom branch when you talk about square roots. When we talk about parabolas, then it's okay because it's a function, right? So we don't have to worry about that for parabolas. What about, let's see. By the way, you can also draw, anyway, we're not going to draw a table for this. Well, sure, we can draw a table for it. So x and square root of x, 0 goes to 0, 1 goes to 1, 4 goes to 2. Exactly. What about x to the 1/3, which is also known as the cubic root of x? How does that look like? Well, it's a lot like the parabola. So for example, the cubic root of 0 is what? The cubic root of 1 is 1. The cubic root of 8 is what? 2, because 2 to the 3 is 8, right? What about the cubic root of minus 8? Minus 2. You see, minus 2 to the cube is minus 8. We didn't have that in here. As a matter of fact, if you put here minus 4, you get not defined, right? So that's new. That's nice. And what it means is that the cubic root, unlike the square root, the cubic root is actually defined over all real numbers. So You guys remember the domain of the function? The domain of a function is the set of what? The set of all possible x values. In this case, the domain of the function is the positive real numbers. Because only positive real numbers and 0, fine. So positive real numbers including 0 are the ones you can plug in. But in this case, the domain consists of all the real numbers, all var. Awesome. Do you guys have any questions on this? No? Okay. So I'm going to tear this out. So you can still see this. Oh, actually. And we're going to talk about a different type of function. Rational functions. F of x equals, what is a rational function? 1 over x is a rational function, yes. What else? Well, 2 over x, that's right. So any function that is the ratio of two polynomials. Polynomials is a rational function. For example, 1 over x, x squared over, x plus 2, or things like that. They're all rational functions. And there's also algebraic functions. Which are made up of any expression. What? Plus? Over?
And minus?
Yes.
Yeah,
and multiplication too, right? Yeah. What about square roots? Yeah, roots too. Anything, any function. You guys remember how we said that polynomials are any function built up using multiplication and addition? So for algebraic functions, we're going to also allow for square roots, divisions, and so on and so forth. Using plus, minus, multiplication, division, square roots, or actually cubic roots, or any kind of roots. So for example, f of x equals, let's say, x squared square root of x squared plus 1 divided by 2x to the 7 plus 4. Okay, so that would be an example of an algebraic function. We will talk about algebraic functions more later, but we're not going to dwell too much on them right now. This would be really hard to draw, by the way. I mean, you could do it, but it would take probably half a lecture to figure out how this function looks like. Okay, then there's also, okay, what am I missing? What other functions am I missing that you would like to bring in here? Exponentials, yes, exponential functions, that's right. So exponential functions. What is an exponential function? Well, something, for example, 2 to the x, that's right. 2 to the x. The way it works is that you take the value of x and you take 2 to the that. So for example, let's draw here 1, 2, 3, and 4. 1, 2. Can you see the numbers? Yeah? Okay, awesome. So what is 2 to the 0? 2 to the 0 is 1. That means that the point 0, 1 is in there. What is 2 to the 1? 2 to the 1 is 2. 2 to the 2. Okay. So the graph has to go through all those points, right? What about 2 to the minus 2? 2 to the minus 2 is 1 over 2 to the 2. That's 1/4, right? So 1/4 down here. Okay, I'm going to try and draw this. Looks more or less like this. Okay, and you can do this with any other exponent. For example, 1/2 to the x, or 1/3 to the x. Again, I'm not going to dwell too much on it because we're just making a review of different functions. So what other type of function? Or do you have any question about exponentials? Yes? E to the x? Yeah, what's e? Okay, yes, but let's talk about e more in detail later. Okay, but that's absolutely right. E to the x is another exponential function. Yes? Trigonometric functions, that's right. So, trig functions. Such as f of x equals sine of x. That's right. How does that look like? It looks like a wave. That's right. Okay, so I'm going to draw here 0, pi, 2 pi, let's say 3 pi. And the function, the sine function, basically goes up and down through those points like this, right? Okay, what about these 2 points here? This is what and what? 1 and -1, that's right. Okay, similarly, the cosine function f of x equals cosine of x looks a lot like it, but it shifted a little bit, right? So let's see, I'm going to draw again pi and 2 pi and 3 pi. And as it turns out, cosine of 0 is not 0 but 1. Okay? And cosine of 2 pi is also 1. So I'm going to essentially go down here and then go back up. And so forth. And then there's tangent of x. So f of x equals tangent of x. How does tangent of x look like? It's a bit harder, right? Okay, so not going to dwell too long on it, but this is pi, this is 2 pi. I'm going to draw an asymptote here. And essentially it looks like this. It looks like exactly like the cubic function, a little bit more, except that a little different. Okay, and then you can keep going. Basically, you can keep drawing the function again and again. Okay, so it's a little bit harder, but you can still draw it. What's the domain of that function? The domain, yes. Is it all real numbers?
No.
It's all real numbers minus what? Minus what? Minus the vertical asymptotes. That's right. For example, there's a vertical asymptote at x equals pi over 2, according to this graph. So pi over 2 is actually not in the domain. Similarly, all the other points that are in the asymptotes, they're not in the domain, but all the other ones are in the domain. Okay. So is there any other functions you'd like to talk about?
Absolute value.
Absolute value. Okay. Yeah. I should have mentioned that last time, but I didn't mention it. So let's throw it in. Absolute value. So absolute value of x is written like this, and it's defined using a piecewise formula. When x is bigger than 0, absolute value of x is just x. When x is less than 0, let's do it like this. It changes the sign. It turns it positive. So overall, I get a function that looks like a v. That's right. So for example, absolute value of minus 2 is what? It's 2, right? Absolute value of 2 is 2. Absolute value of minus 5 is 5, and so on and so forth. Okay? So the absolute value just turns it positive. Great. Anything else? Which one? Inverse functions. Okay, we're going to talk more about them, I think, in a couple of lectures. Yes? Logarithms we're missing. We're also going to talk about them when we talk about inverse functions. Anything else? Okay, yes? Circle? Okay. Okay, so a circle function, written as a function, f of x would be what, more or less? Square root of, okay, square root of x squared. No, not a function. Yeah, I mean, you could make a point that. Let's draw that here. Ah, but I have no markers. Yeah, never mind. Anyway, bottom line is we can include functions that look like a circle, and they'll turn out to look like this. They're algebraic functions. Okay. Let's move on and start talking about how to transform one function into another. So, transforming functions. Transforming one function into another. Okay, so the easiest way to transform a function into another is by adding a constant. So for example, suppose that you have a function f of x. Okay, I'm going to consider it as a graph. And suppose that you have a number, let's call this number c, which is bigger than 0. So what happens when I look at the function f of x plus c? So shifted, okay? Okay, let's think about this. Remember, a function is a machine that takes x, plugs it in some box. The box transforms it into the function f, into the number f of x, and spits it out, right? Yes? That's right. But I'm trying to make you guys or convince all of you why it should be like that and not in some other way. Okay. So for example, the fact that, let's see, this is 1 and 2, and this is 1. Let's say that c is equal to 2. Well, actually, let's make c equal to 1 in this case. So f of 2 is equal to 1. Do you guys agree? F of 2 is equal to 1. What about if we consider this new function, f of x plus 1? Okay? So that new function, you plug in 2, f evaluates it to 1, but you still at 1, so now we have 2. Right? So this function evaluated at 2 is 2. And the same thing with every other number. You take the value f of x and you add 1. What happens is that you end up shifting the whole thing by 1. Does that make sense? Whatever the output of f is, you add 1. So on the Cartesian graph, it becomes 1 higher. Okay? Same thing. If you did f of x minus c, you would shift it where? Down, right? Down by 1. Okay. Now, there's another type of transformation that is very similar. But it's a little bit more tricky. Okay, so suppose that you have a function f of x. Okay, and now you consider the function f of x minus c. So it's almost the same as before. The difference is what? Between minus c above and the minus c down there. No, but let's just look algebraically, right? What's the difference between this thing here and this one here? Yes? That's right. The c is inside the parenthesis or it's outside the parenthesis. Sorry? Exactly. One is taken away from the f. The other one is taken away from the x, if you think about it that way. That makes sense. So it looks almost the same. But now what's the effect of this one right here? Well, I'm going to argue that it's shifting it not vertically but horizontally. Okay? Moreover, and this is something you would not expect, you would usually expect because you see a minus, you would expect that it would shift it to the left. But in fact, it shifts it to the right, which is surprising. Okay. Now let's think, why does it shift it to the right and not to the left? So why to the right? That is why you need to think about things with, it's not enough to just learn by heart that it's moved up. You need to understand why it moved it up before so you can understand why it doesn't move it up now. Okay? Well, one way to think about it is the following. Suppose that you take a value, let's call that value x0. And we want to evaluate the function, this new function, at x0. Okay? So this function evaluated at x0 is equal to f of x0 minus c, right? By definition. So you calculate x0 minus c, and then you evaluate the function f at that point. Okay? So let's say that the function f evaluated at x0 minus c was, I don't know, let's say 2. Okay? So you go, okay, because f evaluated at this point is 2, then this new function evaluated at x0 is also 2. Okay? So the value of this new function at x0 is equal to the value of the function f at the point x0 minus c. And the same thing with every other point. I take this point, the value of the red function here is equal to the value of the blue function here. The value of the red function here is equal to the value of the blue function here. And as you can see, every single point got shifted to the right. Okay, that's the reason why it gets shifted to the right. So why to the right? The reason is that if we define a function g of x equals f of x minus c, the value of g at x is the value of f at x minus c. That's what's going on. So if you do that with every single point, it gets overall shifted to the right. Similarly, if I wrote f of x plus c, it would also get shifted but to the left, not to the right, exactly. Okay, let's do an example of this. So sketch the graph of f of x equal x squared minus 6x plus 10. Okay, so the first part of the work is algebraic. We would like to factor that thing out so we can see very clearly what it looks like. Okay, and if in order to factor it out, we would like to use these binomial formulas, right? So I'm going to write the binomial formula over here just for you guys to remember. Binomial formula is, let's say, let's write it like this: x minus a squared is equal to x squared minus what? 2ax in this case, plus a squared. Okay, so what? If you just look at this, x squared minus 6x, what do you think would be a? 3, right? So you would like to use this formula and factor it out. So x squared minus 3 times 2x, okay? So you say, okay, great, binomial formula with a equals 2. But what happens? On the right, you have a 10. You don't have a, you want a 9, right? Okay. So this technique that I'm going to tell you is known as completing the square. I think it's completing, right? Yes? Okay, completing the square. Okay, fine. All right, so completing the square means we're going to put the 9 in there. We would like to have a 9 in there so we can factor it out. And if there's not a 9, there's a 10. So I'm going to add 9, and then I'm going to subtract 9 again. Okay? So this is equal to, x squared minus 6x plus 9 plus 10 minus 9. And these three things together, we can factor out as x minus 3 squared plus 10 minus 9 is 1. Awesome. This is pre-calc, so I'm not going to spend too much time in it, but that's the way to factor out this kind of term. And once you factor it out, you can recognize that it looks a lot like the function x squared. But something has been done to that function x squared. It's not the original function x squared. Okay, so what does the plus 1 in the end mean? Plus 1 in the end means that it's the parabola is shifted to upwards by 1. And there's also, instead of x squared, there's an x minus 3 squared. You see it? You see, just like, what's your name again? Just like Peter mentioned, I really liked it. the 1 is changing the whole thing, whereas the 3 is only changing x. Okay? So in that sense, we can draw the following function. So this is the function x squared. Okay? This would be the function 1, 2, 3, okay? This would be the function x minus 3 squared. Everybody agrees? We've shifted it to the right by 3, right? And now we're going to add 1 to the whole thing. So it becomes x minus 3 squared plus 1. Yes?
Why did it shift to the right instead of going to the left? It was a negative 3.
Ah, we were just talking about that. We explained here in this graph right here. For c positive, okay, so in this case c equal to 3. You write the original function f of x, and when you write x minus c, the function gets shifted to the right. Okay? So it's just what we explained before. It's shifted to the right instead of to the left. It sounds like it should be to the left, but because it's inside, because it's modifying x instead of f, it's shifted to the right. Okay? Yes?
Here we now use the formula f of x equals a of x minus h plus k.
A of,
X minus h in parentheses plus k.
yeah, it's the same thing.
Yeah, but sometimes it helps for other people.
Okay. Yeah, but yeah, but it's pretty much the same thing that I wrote, right? You know, that when you write minus h, you're moving it horizontally by h, and when you add k, you move it up by k. Okay? It's the same thing. Okay, so we still have a few minutes. So we get to talk about compositions. So what is a composition? Suppose f of x and g of x are functions. So what we're going to do is imagine again a function as a machine. So you start with x, you plug it into this black box called f, the machine f, and out comes f of x, right? Now here's the machine g. Okay, so you plug this value that happens to f of x, you plug it in here, and out comes what? G of f of x. That's what we call a composition. It's one machine after the other. It's like you have a whole factory of functions. One machine, you plug it into the other, and you have more complicated functions. So for example, by the way, this thing we call g composed with f. You might have seen this notation before. The little ball in there means composition. So g composed f with f is the same thing. Don't be scared about the little ball. It's just g of f of x. That's all it means. Okay? So for example, if f of x is x squared plus 1 and g of x is equal to sine of x, then what is f composed with g of x? Okay. Well, let's do this carefully. Okay, so it's f of g of x, but we know that g of x is sine of x, right? So it's f of sine of x. And remember, f of anything is anything squared plus 1, right? Whatever you plug into this machine, out comes that thing squared plus 1. So this is sorry, sine x squared, sometimes we can write this like this, plus 1. Sine squared of x plus 1. Okay, what about g composed with f of x? Is it the same?
No.
Who thinks it's not the same? Okay, who thinks it's the same? Okay, you're good. It's not the same. Okay, g of f of x is equal to g of x squared plus 1. Remember, f of x is x squared plus 1, right? So g of that is sine of x squared plus 1. Very different from the other one. So we can conclude that, I'm going to write this over here, but you can write it on the bottom, is that f composed with g is not necessarily g composed with f. You should keep that in mind. And we're done.